تمام كده أعتقد الشاشة عندي واضحة.
Yes, it's okay.
طيب. إن شاء الله today in this training we will make a 3D model for this equipment which include a hemispherical head with negative straight flange, forged nozzles with lips. But before starting this demonstration, inshallah, we will discuss some important points regarding SEG software and how we can deal with the interface, selecting the module of modeling, like if we would like to make a pressure vessel or heat exchanger, storage tank, spherical tank, something like that, how we can select between different modules which they are available in SEG software. Bismillah ar-Rahman ar-Rahim. In this training today, inshallah, we will discuss some points regarding to SEG user interface, SEG available modules, how to create a new project, how to there is a difference between the main parts and the childs, how we can select the main part and how we can add a child to this main part. The user coordinate system concept in SEG software and Autodesk Investor. The unreal elements and some of common mistakes that we will learn how to avoid making them. Here for the user interface, we have some toolbars. The main toolbar at the top. This main toolbar includes some buttons. Those buttons give you the ability to make some orders, like creating a new project, open an old project, and you can add elements from here. Okay. On the left-hand side, you will find a tree view. I can hear my voice. There is some echo. Would you mind to mute the voice from your side? Okay. On the left-hand side here, there is a tree view. In this tree view, you will find the project data, like adding a new equipment. Inside this equipment, you will add the elements of this equipment, like head, shell, cone, nozzles, saddles, skirt, like that. On the main area at the middle, you will find the dialog box for each node. You will select it from the tree. Like if you select the project node from the tree, you will find the project information here on the middle area. So you can define the project information. If you select the equipment node from the tree, you will find the design data of this equipment, so you can fill it. Any other point, you will find the interface of this node. Like if you have a head, you can select the type of the head and fill the dimensions of this head. Here at below, you will find the license period, and on the right-hand side, you will find the toolbox. This toolbox gives you the ability to add elements, like Elements tab here on the main tab. Here's some of the toolbars available in SEG, like File tab, which include adding a new project or open an old project, save as an old project, changing the project type, like in a stage in your project, you would like to change the equipment type from a pressure vessel to a heat exchanger, something like that. You can make that by changing the project type. On the element type, you will find the available elements. As we discussed on the previous slides, you have a main elements, which is they are the parents, and childs, which is they are the attachments for those main elements. And we will discuss that during the training also. The assembly tab, edit tab. In this tab, you can reset all the model, reset one part, something like that, and we will discuss that in detail, inshallah. On the setting tab, you will find the equipment setting, From this one, you can change the equipment setting, and from the app setting, you can change some options like making the sorting of the bill of material, rendering during rendering, and units which will appear on the bill of material and your drawing. On the last tab, which is tables, you can open and edit or export to your drawings the bill of material table, nozzle table, and many other tables. And by the way,
Mr. Ahmed, we cannot hear you.
Your voice is gone.
Mr. Ahmed. Hello?
اللهم صل على النبي. I think now you can hear me.
Yes.
Okay. It's from the beginning or just from seconds? Mr. Khalid.
Just a second.
Okay.
Yeah, just a minute. Okay.
So why it's muted? I don't know. Okay. So let's come back to this slide.
Move after this one. After this one.
Before that one. Okay.
No, after.
But we still on this slide. I didn't finish it yet.
Can you go back?
That one?
And bill of material, yes.
Yes.
Bill of material tables and tables, yes.
I think there is a delay. Okay. Here for the tables, you will find okay, I can hear my voice. Would you mind to mute from your side? Okay, for the tables, you will find many tables. You can export it to your drawing, and you can make a review for it, and you can export it in Excel format. And by the way, you can generate an estimated material cost report. From the user interface, you will need to define your profile. Here, from the profile, you will need to define your name, your telephone number, and your email, because those information, if you would like to make a bug report, those information will be reflected automatically, so we can know who sent this email and reply to the email address that's sending this email. Okay, you can select between different skins available in SEG software. There are more than 20 different skins available. You will find a tutorial button, so you can listen and watch to the videos directly from SEG application, or you can open the YouTube channel from this button. So it will be open on your browser, so you can go through the channel and check the training videos and the live sessions. The template tab, you will find some pre-built projects. You can check them and check how they are created. The next step is the available modules in SEG software. As you can see from the main form of the creating a new project, you will find pressure vessel module, okay, a horizontal and vertical pressure vessel, a heat exchanger module, ducts module, storage tanks with fixed roof, spherical tanks, and piping. If you select a pressure vessel, for example, you will not be able to create a tube sheet for baffles, which they are available in heat exchanger, expansion joint. So if you select a pressure vessel, you will not be able to make the heat exchanger elements. The same for tanks. If you select a pressure vessel, you will not be able to make a roof or annular plates or clean outdoors on the vessel. The same for ducts. So for the overall module, you will be able to generate all of those items on the overall project. The overall project gives you the ability to reach the roof plates, the heat exchanger elements like the expansion joint, tube sheet, the spherical tanks elements, and duct elements. For the project data, after creating your project, you will need to define the project information like project number, project name, client. All of that can be reflected to your drawing. So if you would like to reflect that automatically from SEG to your title block, you can do that by filling those information. If you have let's say a fixed title block and you will fill it manually, you will not need to fill that from SEG. It's up to you. So if you would like to reflect those information directly to your title block, so you will need to fill it. For the equipment and the design data. On the second level, here for the equipment level, after adding an equipment, if you select this equipment, you will be able to define the design data of this equipment, like the construction code, the internal design pressure and the temperature, the external design temperature and pressure, maximum allowable internal and external working pressure, minimum design metal temperature. All of those values you can edit and modify the values. And if you have an Excel sheet, you can import those values directly to SEG. The equipment setting. For the equipment setting, you can select between different positions for the vessel. Like if you would like to make your equipment in a vertical or horizontal or tilted position. So from this drop-down list, you can select the position of the vessel. If you would like to make it a vertical vessel, horizontal or tilted vessel. And you can select the direction of the assembly. So you, in horizontal case or tilted case, for example, you can start your assembly from left direction to right direction, or flip it to make it from right to left direction. The same for vertical. You can start it from bottom to top or top to bottom. Okay. Here for the details of the equipment, you can define the service of the equipment, the tag number and serial number of this equipment. And for the delivered blade dimensions, by using those values, SEG will calculate automatically the number of blades required for the shell course. Okay, so if you have a large diameter vessel and the available blades in your stock, length and width will not make the complete circumference or the complete shell diameter. So SEG automatically will calculate that and calculate the required number of blades to make the complete circumference of the shell. You can control the data entry units if you would like to import it in millimeter format or inch format. Here are some of the main elements available in SEG software. If we take a fast look here, you will find the head. This head, you will find more than 17 types of heads, like hemispherical head as a half of ellipse, or ellipsoidal head, including ellipsoidal head as a half of ellipse, or ellipsoidal head including crown and the knuckle radius, head as a closed-end cone, and we will discuss the available types of the head. The same for shell. If you select the shell, you will find a different types of the shell. Suits many different conditions, like suits storage tanks, suits heat exchanger or pressure vessels or piping. Some other available elements like fittings, like reducers or elbows or T's, flanges and gaskets for heat exchanger with pass partitions, extension joints, storage tanks elements, and spherical tanks elements, and duct elements. Here for the attachment, we're talking about a concept of parent and child. The parent element means the main element of the equipment, like head, shell, cone, which makes the main body of the equipment. And the child is just an element attached to the main element. So, for example, here, if we have a head, so if you select this head, you will be able to add some of those childs. They are defined in groups, like a child supports. So you can add a skirt to this head. You can add a support pipe as a leg to this head, support beam as a leg to this head. Another group, which is nozzles, so you can add a nozzle with external projection to this head, add a nozzle with internal and external projection to this head, weld OLED couplings, and stud outlets. You can add internal attachments like impingement plates, vortex breaker, pass partition, clad. You can add external attachments like insulation clips, add a lifting lugs to this main element. So when you select the main element from the three, you will be able to add some of the available attachments here. Another case for shell, for example, when you select the shell from the three, on the Elements tab, you will be able to add supports like saddles, stacked saddles, legs, lugs, skirt. So you will find those attachments available here. And for nozzles, you will find those type of nozzles. And lifting lugs, external attachments, internal attachments, platform, and coils. For the orientation of the attachments on the main elements. In the case of horizontal vessel, you will be able to define the orientation as mentioned here. If you take a look from the back view for this equipment, 0 degree will be at the top and 180 degree will be at the bottom. 90 degree will be at the right hand side. So the orientation will be on the clockwise direction. For the vertical vessels, if you make the lock to be at the top by that way, and the top is flipped 190 degree, the orientation of the nozzles will be like that: 0 at the top and 90 degree will be on the right hand side. So for the case that we have, if we take a look to this vessel, for example, if we take a look from the back view, that's a horizontal vessel. So those nozzles will be at 0 degree. All of those nozzles will be on 90 degree. Okay, some of them with heliside offset. Okay, and some other nozzles at 180 degrees, and some nozzles on 270, some of them with heliside offset like that. Okay, let's come back here. The concept of the user coordinate system. In SEG software, we have a concept to make the parts arrangement or the assembly arrangement by arranging elements after each other for the main elements. Like if you have a flange, this flange has start point and end point. So to connect it with the next part, you will need to connect the end point or the end UCS at this element with the start UCS of the next element. The same for the shell, for example, you need to connect the start UCS of this element to the end UCS of this flange. So that's the concept of the assembly. The concept of the location or the reference point for each element. Here in this example, we have this nozzle. So in the data sheet or in design software, you can define this nozzle from the tan line, for example, or from facing of a body flange. But here in SEG software, you will need to define the location of this element based on the start node on the main element. This nozzle located on this shell. So the reference point from the center line of this nozzle will be referred to the start point of this shell, not to the tan line, because this element cannot see the tan line. It's only seeing the main element, which is the shell in this case. So you will need to define the location of element based on the reference point of the main element. Some other concepts here for the gap and overlap. How we can make a gap between elements. Sometimes we need to make a gap between elements and make overlap between elements. We will have some unreal elements. Let's say it's not a real element. It's unreal element. You can use it to make this overlap or making a gap. For example, if you have this head and this shell, and you would like to make a gap between them, let's say with 4 millimeters, more or less. I'm talking about the concept. You need to make a gap between them, so you can use this type of part, which give you the ability to make a gap between elements. When we talk about the concept of the user coordinate system, this gap will give you the ability to move the user coordinate system from the end of the head to the end of the gap that you need. The same thing for the overlap. Here, if we don't add this overlap here, this cone will directly connect it to the end of this shell, not like that. But by adding this part, which is the overlap, that will give you the ability to move back the end UCS of the shell right here with your defined distance. So you can move back the overlap and start your next element from the new end point, not the previous end point, which is the end of the shell. I hope this concept become clear now. Okay, some unreal elements in SEG software. There are some unreal elements. You can use them to add attachments to some other childs. For example, if you have a nozzle connected to another nozzle or a coupling connected to a nozzle neck. As we discussed, you can add a child to a parent, not to another child. Okay, so how you can add a coupling or let's say a child to another child? By using this concept, which is adding a real element, this option will give you the ability to add a child to another attachment, and we will discuss that during the session. Some of the common mistakes. One of them is creating a project by and selecting some illegal characters like backslash, star, question mark. Those are illegal characters. So Windows cannot create a folder or a file including a character like that. So let's check that. If we create a new folder, for example, and let's try to add a backslash. Not backslash here. Let's add question mark. Same thing. So there are some characters. We can call them illegal characters. So some of those mistakes which making a project by including a character like those. Let's check that. Here, let's create a new project. So from file, let's add a new project. And from here, let's select a project like, and let's add 2 question marks and 2 backslashes like that. And let's create a new project on the desktop. Now, if you try to click finish, you will receive this message, which is illegal characters in path. So you will not be able to create a project with that character because SEG tried to create a folder like this, and the Windows will stop that. Okay, that's the one of the common mistakes, which adding illegal characters. The same thing for the nodes here. If you named your vessel or your elements with a character like that, when SEG try to create a part including that name, because SEG creates those parts on Autodesk Inventor. So if you add a backslash or a question mark to the name of the head, for example, when SEG try to create this part and save it, the Windows will prevent that. Okay, so you should take in your consideration to avoid making names with illegal characters. Okay, the second mistake, which renaming the project folder by hand. This mistake is a really common mistake because it's making some of issues, and the user will conflict why this issue appears, and to me, I didn't make anything. Let's create a new project like demo, and make this project at the desktop, and let's click on finish. Okay, now SEG will save the current project and close it, and open the new project, which is demo. Here, if you take a look to the desktop, you will find a new project called demo, and this folder includes assemblies folder. So all assemblies will be generated here on this folder. Parts folder, all parts will be generated here, and the drawings and building details will be generated here. Here you will find, if we increase the view a little bit, here you will find the SEG file, which takes the same name of the project. So that name, which is demo.seg, looks like the name of this folder, which is demo. Okay, so the names should be the same. Okay, and the IBJ folder for Autodesk Inventor should be the same. In all the versions, you will find the same name here for the backup file of the project. Let's close this project here. Let's close this. Let's close SEG. All close SEG. And from here, let's name this folder. Let's make it demo of. Sorry. Like that. You can figure that we change the name of the folder, but keep the names here inside as they are. Okay. The project file, the project name here, not changed. The Inventor project file, not changed. So if you would like to open this project after naming it, so let's come back to the desktop and open this demo folder. So let's open this one. You will receive this message, which is telling you that the project name is demo, not the current name. And in that case, you will not be able to make anything to your project. You will need to change the name again to the old name. Okay, so let's close this. Sorry, let's close the project. And here, if you, sorry, I think we will not be able to close that. Let's delete this temp file. If we rename all files to the same name, let's come here and change all names like that. So you can figure that we make this renaming manually. This renaming, we did it manually. Make this name looks like the folder name, but you will still facing another error or another issue if you would like to open this project, because the stored name of the project inside this file not looks like that name. So if we open SEG Software, okay, and from open, let's open this project. You will not receive this message, but if you would like to add an element like head, for example, let's add head. And when you click on add, you will receive this message, because the name of the project inside the SEG file differ from the name of the path of the project. So to avoid making that, how you can take a copy from a project to another project and make some editing, like if you have two typical vessels with different names and different orientations and locations. So how you can do that? So from SEG Software itself, you can make save as project. By that way, by using this option, you will be able to save another copy from your project with a different name. Okay, so don't make a renaming manually for the project folder or for the SEG file. Let's close this and let's complete the this form. During creation, you will need to send the commands to Autodesk Inventor to create the parts and assemblies. During that, avoid making any saving during sending commands, because during this process, SEG sending commands to Autodesk Inventor and receiving information to store it in SEG file. So during this process, if you click on save, you may cause a problem on the SEG file itself. So during sending commands, avoid making clicking on the save button. That's one of the common mistakes. Selecting another node without checking the appearing form. For example, if you selecting move from a node like head to another node like a shell, you should be sure that you selecting the shell icon, not the shell text, and the form of the shell appear on the drawing area. Okay, because sometimes and there is some delay, you may still receiving the head form instead of the shell form, and you make some changes and make a save during that, and after that you will figure out that you was selecting the head, not the shell. Okay, so you should be sure that you select the correct element from the tree. Another common mistakes, which is making an element same as another element after creating the Autodesk Inventor model. We will check that during the demo, inshallah, because this option you can use it before creating the Inventor part, but after creating the Inventor part, you can make it by another way, not the traditional way. Sometimes when you, the last common mistake, some elements may stuck in the memory. That may take place when you change the type of the element. Like, for example, if you have a shell as a part from one element, after that you decide to change it to make it as assembly from different elements. In that case, Autodesk Inventor itself will still catch the last part in the memory, and to release that you will need to reset this element and close both of Autodesk Inventor and SEG software. That's not happens anytime, but sometimes if you facing an issue regarding that, you may need to close SEG software and Autodesk Inventor to avoid receiving an issue or an error regarding part changing or type changing. Here's some images regarding the project name or element name, which include the illegal characters. You will receive this form, which is illegal character path. Here for the if you would like to, if you make a hand rename for the project folder, you will receive this message. And if you make a renaming, manual renaming for all files like SEG file, project file, you will not be able to add elements and you will receive this form. Okay, now let's close this and let's start a new project. Okay. Okay, now we have we open the SEG software, and inshallah we will create a new project. In this session, inshallah, we will discuss how to make this 3D model of this equipment and how we can edit and modify if we would like to add some external attachments not including in SEG software. We will discuss some of those points inshallah. Okay, from new button, let's create a new project, and from name here, let's define the project name. So that's the project name, and from here, let's select the location of the project. Let's add it on the desktop, and from here, let's select the module of this equipment, and let's select a horizontal pressure vessel and click on finish. Now, if you take a look here to the desktop, you will find a new project created with the name of the project. As we discussed here, you will find those folders, which they are the folders of the project for the assemblies, parts, and drawings, and the SEG file, and another Autodesk Inventor project file. And there is another hidden file for the backup. If you show the hidden files, you will find a folder for the backup folders. So if you face some issue, you can get the previous backup from the SEG project. But right now, let's create or name this equipment as a horizontal vessel, for example. And if you select the project node from the tree, you will be able to define the project information like project number, project name, plant name, client, all of those information. After changing them, you can save your project, save those information. From here, if you select the vessel node from the tree, you will be able to define the design data of this equipment, like the construction code. By the way, you can double click on the cell and modify the value like that. So you can edit. Like that. So you can go inside the cell itself and redefine the value. And from here, you can define the units. You can select if you would like to export this value or not. So from this box, you can select the required values only that you would like to export it to your model. And you can import values from an external Excel sheet. And this Excel sheet should be in 3 columns, and each column should be filled. Like, let's make an Excel sheet like that. And let's open it. And let's define the value of the first cell, like construction code, like that. And the third cell, so will be like that. So you have 3 columns. The second column, the design pressure, 0.2, and the unit is megapascal. Design temperature. So like that. Sorry. See, so to make it in degrees, you will need to write it by that way, which is C and percentage, and D. So to make it like that, so that to make the Celsius or Fahrenheit, to make volume مثلا. Okay, let's say it's meter cube. So from here to add a cube, you will find here this. You can use those characters to add to the power 3. So like that. So you can get meter cube like that. So if we save those values and close this file, if you come back here to import from Excel and come back to the desktop and select this Excel sheet, you will find that you will be able to import your Excel sheet to the model here. Okay. And after that, clicking save to save the information, but we will not save that. Okay. After creating this visit, from the setting tab, if you open the equipment setting, you will be able to define the service of this equipment, the heat treater, and the serial number is 500. And it's when you select the module as a horizontal vessel, automatically SEG make the position of the vessel as a horizontal and make the arrangement start from the left to right direction. From here, you can define the available blade dimensions. Like if you would like to define the length of the delivered blade as 9 meters, so you can change it from here. And the same for the available width. So SEG will use those values to calculate the required number of cells. Now let's save those information. Click on save. Now let's add a new element. By the way, here if you select the element tab, you can add elements from here from this toolbox, or you can add directly from elements. So I prefer to close this toolbar to save some area on the drawing area here, to save some area. So if you close this, and if you would like to open it again, for example, here you will find the show toolbar. So this toolbar will appear again inside. By the way, this toolbar is a floating toolbar. You can move it here or there, for example. So you can move this toolbar in another places like that, or make it on the middle, or make it on the right hand side. So on the default position, it's on the right hand side. Let's close it. And from here, let's select the equipment node from the tree. And from elements, let's add the first element, which is head. So let's add a lift head. And from here, you will find a list of available heads here. For the first type here, you will find an ellipsoidal head as a half of ellipse. If you take a look to the image on the right-hand side, this type of head is a half of ellipse, not a head including crown or knuckle ridges. But if you would like to make an ellipsoidal head with crown and knuckle ridges, you will select the second type, which is ellipsoidal head with crown and knuckle ridges. And for this type, you will find the crown and knuckle radius values appear here on the red font. So the crown radius here is 0.9 from the ID, and the knuckle radius will be 0.17 from the ID. So this type, which is ellipsoidal head with crown and knuckle radius, those values are constant. So when you change the inside diameter, the crown and the knuckle radius will be calculated according to those equations here. But if you would like to define the crown and the knuckle radius manually, you will need to select the user-defined crown and the knuckle radius. By selecting this type, you will be able to define the crown radius and the knuckle radius manually from here. There are some other types like flat dashed head, and here the equation for the crown radius calculation and the knuckle radius value. For the standard type, the equation for the crown radius and knuckle radius value. Semi-elliptical head, the values for crown and the knuckle radius. Spherical head for crown and the knuckle radius values will appear here. Another types like standard cap. So if you would like to add a fitting like a cap, you can add it from here. Diffuser head, convex head, like in the heat exchanger on the floating head. Flat head, hemispherical head with a straight flange, so you can add a straight flange to this hemispherical head. There is another type, this type we will use it in our model today, inshallah, which is a hemispherical head with a negative straight flange. This type usually used in division tool, and you can figure that the center line of this head lies after the cut with a negative straight flange, and this straight flange will be located on the shell itself, not on the head, and we will discuss that in the 3D model here. If we, for example, if we take a look to head here, you can figure that the center line of this head lied after the cut here. Usually, the head include a straight flange, so the end of the head could be at that line. But for the head with a negative straight flange, you will make a cut on the head with a negative value, and this straight flange will be on the next element, which is head. Let's close this and come back to SEG. Let's complete the other types of heads. Here you can add a cone head with a neck at the end like that. So you have crown radius at knuckle radius at the start and knuckle radius at the end. You can add a cone with a closed end like that. A cone head with a crown radius at the end only. You can add a circular flat end or a hold circular flat. For our case, let's select a hemispherical head with negative straight flange. And let's define the inside diameter of this head as 4 meters. And the thickness of this head will be 16 millimeters. And for the shell thickness, it will be 190 and 80. And for the minimum thickness after forming of this head will be 60 millimeters. Here one more option we will make it. which is making this head from pieces or segments. If you take a look to the head here, it's not including any welding lines. So if you would like to make it from pieces, you can select 2 pieces to add a welding line like that. Or if you would like to make it from segments, like in our case, you will select this option for that head, which is more than 2 pieces, and define the cut ID. If you take a look to the image on the right hand side, so take print screen from this, and let's increase the view. So you will need to define the
Mr. Ahmed,
yes.
can I ask one question here?
Yes.
Okay, for this specific case which you are just presenting, in this one you put it the ID of the tank, this vessel ID. Okay.
Yes.
Now I can see this the hemispherical head. This is not complete hemi. I mean the line which is showing the weld line at the point of the weld, it is not complete hemispherical. I
Yes.
believe it is some part of it. It is cutted and it become the part of the shell.
Mhm.
So the diameter of this hemi head also equal to the shell ID, or it will be
No.
more.
It will not equal the shell ID.
It will be more.
Yes, should be more.
So
And
how
we will
we
check
define
that.
it?
We will check that. It's automatically calculated based on the
Offset
difference
value?
between the shell thickness and the head thickness. Okay, it's automatically calculated based on the difference between shell thickness and head thickness. Okay, and I will show you how we can get it now. Okay. So from here, let's define the cut ID. Here, so let's define this value, 3 meters and half. And here, that's the gap between elements, which is the weld gap. If we take a look here, if you take a look to the image like that, so the difference between elements from this segment and that one. So if you would like to define the gap as 0, you can do that, and you can define it. That's because those are different elements. If you have one element including one welding line, you should define a gap for the weld, and we will discuss that inshallah during the creating the other parts. But right now, let's keep this value as 2, and let's define the longitudinal welding line orientation to be at 45 degrees, and from here let's define the number of segments to be 4 segments, and let's click on save. From the setting tab, let's discuss some points here from the app setting. One of them here for the rendering or for the preview. If you would like to make a rendering for groups during creation or parts, main parts during creation or childs during creation, you will need to select those checkboxes. Those checkboxes will give you the ability to make a rendering for elements during creation. They will not be created on behind after that appear on the final assembly. You can control the icon size, so you can make it mix it. So the first icon will be the large icon, and for the other icons will be small, or you can make all of them as a large icons or all of them as a small icon. That's related to the icon style. Here for the zoom extend, you can make the zoom extend as a auto in the auto option. So after making the assembly, the Autodesk Inventor will make a zoom extend for all of the view automatically. But if you would like to make it normal, you wanted to make this control by hand, so you will make it in a normal position. For the units in your bill of material, you can control that from here, and we will discuss that in detail if you would like to make the units in millimeter or inches, or mix between millimeter and inches. Select the format of that. The same for the nozzle size if you would like to make it in NBS or DIN, or you can make it mix. The same for grouping bill of material if you have more than one equipment. Now let's save those options and click on save. Now, if we open the create the 3D model of this head, you will find that that's the first segment of the head, and the other 4 segments shall be generated and assembled to this head. Okay, here you can get this head, which include 4 segments of elements. Okay, if we open the assembly here, you will let's open it in another form. You can figure that you have each segment of the head as a separate segment, like that, as a separate part. Okay, and you can figure that from the tree, so you have those elements of this hemispherical head. Now, if we come back to the bill of material and check the bill of material of this element, you can figure that the this element, it's a hemispherical head. Okay, and here you can figure that the inside diameter of this head, it's not 4 meters, it's more than 4 meters, it's 4058. So that's the calculated inside diameter of this head based on the straight flange and the difference between thicknesses between shell and head. Here you have the thickness of the head and the minimum thickness after forming and the cut length on the head. Okay, it's 3:1 or 1:1/3. The slope of the cut, and here that the cut value. Okay, now let's add another element to this vessel, which is another main element, which is the can. So let's build the vessel body, like heads and shell blades. After that, we will proceed, inshallah, by adding the attachments to this head. So from here, let's add the second can. So from here, let's select the equipment node from the tree, and from elements, you will figure that you can add another main elements. But if you select the main element, you will be able to add childs, like what we discussed on the slide. So from the vessel, let's add a can. Let's add can 1. Okay. And from can 1, you will find many different types of shell blades. Like if you would like to make it from a standard pipe, so you can select the standard size of the pipe. After that, select the schedule. And if you would like to define the thickness of this pipe manually instead of standard schedule, you can do that. A welded pipe, it's the same dimensions of the pipe, but you can add a welding line to it. Another type, which is shell without welding lines. So you can use this type, actually, and use it in cases like making an offer. So you would like to get a quick render for the model, and you don't need to make everything in detail, just a one shell course with constant thickness with a huge length, like in LBGs. For example, if you would like to prepare an offer and you would like to get a weight for this element, and you don't like to make it in detail. One of the most common shells, which is the shell. In this type of shell, you can add this shell as a one part. And if you defined the inside diameter here, automatically SEG will calculate the required number of plates to generate this shell course. Okay, let's try this. So let's make it 400 millimeters, and let's click on save right now. After that, we will reset this element. But from here, let's create this element. Automatically, SEG detect that what is the diameter? Okay, So based on the defined setting here, if we open the setting of the equipment, I defined the length of the blade as 1 meter point 2. Okay, so here if we open one of those blades, let's open the assembly of the shell. So if we open any one of those, okay, and get the sheet metal development for this one. So after getting the shell development, if we measure the blade length, you can figure that it's 1.2 meter. Okay, that's the delivered blade or the available blade dimensions in your stock. So SEG automatically calculate the required number of blades. So they will be all equal, but the last one will be calculated. The length of the last one will be differ. Okay, so let's measure it separately. So from here, if we get the inspect button, and from here, let's measure that. So the last one will be with a differ length, which is 575 millimeters, which we will need it to make the complete circumference of this shell course. Okay, so let's define this value like that and click on save. Here, for the main element like shell, we need to reset all the model, or make a reset for this element, but we will need to close this SEG and open it again. But here, let's make reset model because we don't have a lot of elements. And let's click on start. As you can see here, after changing the available blade dimensions, this shell now created from two pieces. The first one with 12 meters length, so that's the first part. If we get the shell development for this one and measure the length, it's 12 meters, as you can see. So which is the available blade length, and the other one will be calculated automatically from SEG. Now let's create the suitable pipe for our case, but before that, let's discuss some of other options. Let's reset the model, and from here, you can add a shell to suit the hemispherical head according to division 2, and this type includes the chamfer based on the thickness of the shell and the thickness of the head. Okay, another type, which is shell from different pieces. This type you can use it in case of storage tanks, because that type gives you the ability to define each blade length and thickness. Okay, blade length, sorry, and control the longitudinal welding line of the start welding line of the first part, and automatically the other angles will be calculated automatically, and we can discuss that on another element in this project. You can add shell from different pieces and the thicknesses, or sloped for tilted vertical storage tanks. If you have a tilted vertical storage tank, you can use this type. So each type of those you can use it in a certain case. In our case, let's select a shell to hemispherical head with a negative straight flange, and let's define the inside diameter, define the thickness of the shell, the longitudinal welding line orientation, and the length of this shell course, has a gap between elements, and let's make it from more than one piece. And by defining it by that way, you can make it with as equal pieces. So you will have two segments from this shell, and both of them are equal in length. Here, that's the shell thickness, and the chamfer will be to the head. So we will not select this checkbox. Now let's click on save, and let's add another can. Okay, so from here, let's add can 2 and click add. From here, you can select this type of shell, define the inside diameter, the thickness, and the longitudinal welding line orientation, the length of this one. Sorry, make it 80 degrees, and the length of this one will be like that. And let's make it from two equal segments, and click on save. Now, what?
Inside diameter of the first can need to update.
Okay, sorry, it's okay. So let's define it to 4 meters instead of 0.4. Okay, and let's add another can, but in that one, we will define this can as a shell from different pieces, so we can control each plate length. So from here, let's add a can 3. But from the type, let's select shell from different pieces. Okay, that type will give us the ability to define the number of blades and to control the length of each blade. So from here, let's define the inside diameter. Let's define the length of the course, define the thickness, and from here define the gap. Let's make it 2 millimeters, and the number of segments, let's make it 3. And for the first one, let's make it let's say 7 meters, and for the second one, let's make it 4 meters, for example. And the longitudinal welding line orientation, let's make it on 60 degrees, and click on update. So here you can figure that the first part length, or the first shell plate length, is 7 meters, and the start angle is 60 degrees. And here the calculated end angle of this part. The second part length is 4 meters. So the start angle will be the end angle of the first part, and here the end angle longitudinal welding line of this part, and here the last one. So if we make that one as 2 elements and click on update, you can figure that the second part will be calculated automatically, and you will get you can control the blade length in case if you would like to make that. Okay, so by using this type, which is shell from different pieces, you can control the length of blade. From here, if you click on update, so you can get to different pieces by that way. But let's come back to shell and make that value as 4 meters, define the inside the thickness, the longitudinal welding line orientation. The length will be, and the gap will be 2, and number of segments will be 2. Now let's add another can, which is can 4. In that case, we can make the parts looks like another part by selecting same as. From here, we still not generate this element, which is can 4. So you can make it looks like another part. So from here, you can make it looks like can 2. If you select add, if you select can 4 from here, you will find the same information here, and you can make some changes like changing the longitudinal welding line orientation and the length of this can, and click on save. Now let's add another can, which is can 5. And let's make it looks like can 3. So can 5 longitudinal building line orientation will be 70, and the length will be 400. So save another can, which is can. So the last can. Okay. Let's make it looks like can 1 because it will be connected to another hemispherical head with negative straight flange. So let's select can 1, and from here select same as can 1. And from here, if you add this shell, you can figure that it's a shell to a hemispherical head with negative straight flange. Okay, and from here we will select this option to make the chamfer on the other side, and click on save. Now let's add another cab or another head, which is right head, and let's make this head looks like the left head. So if you select it, you can figure that it's a hemispherical head with negative straight flange, the same dimensions. But in that case, we will flip the convex direction of this head to the other side. So let's select this option and click on save. Now let's create the 3D model of this equipment. The first can parts. If you would like to make a change for some elements during creation, you will need to stop the assembly to avoid any mistakes. So here we would like to make a modification, so you can make a stop and wait until this process ended. So it's can 5. So now it's after creating this element, you can figure that this button become blue again. So you can make a modification here. So let's select can 6 and make a modification on the longitudinal building line orientation and change the length of this one to be like that, and click on save. So that's the way if you would like to stop the assembly and make a modification. By that way, by clicking on stop button and wait until this button activated again, and you can now start the assembly. The last can. Okay, now we have the 3D model of the equipment, main parts of the equipment, which they are the head and shells. Now let's add some attachments to this model, like adding saddles, trunnions. After that, let's add the nozzles, inshallah. Okay, so from here, let's select the first can, which is can 1. And from elements, you will figure that you can add those attachments like for supports, as we discussed on the PowerPoint presentation. You can add, you will find some groups here like supports group, nozzles group, lifting group, internal attachment group, external attachment group, and here internal attachment group, platforms, and coil. From here, let's add a support saddle. So from saddle, let's add this type of saddle, which is lift saddle. And for that, I would like to discuss some options and types of saddles. Okay. So in SEG software, you will find four main types. In each type of those, you will find three sub types. For the first type here, you can see that you can add outer ribs and the web is directly connected to the shell without any edges here. For the second type, you will find a straight edge here. This edge goes to the center of the vessel. The end of it goes to the center of the vessel. And the third type with this straight edge, and that edge is perpendicular to the base. And the fourth type with saddle with the lifting lug. So for the first case here, the web not include any edges like that, and you can add outer ribs by that way. The three sub options, which they are making this saddle aligned to left or aligned to right, or you can make the web at the middle by that way. Some other options, you can control it by controlling the bottom width. So you can make this saddle with straight edges, or you can control the bottom width, so you can make it with a narrow or wide bottom like that. The second type includes the same options, which is aligning the web to the right direction or to the left direction, or you can make it on the middle. As you can see, this straight edge goes to the center of the vessel here. And that will give you the ability to make the sides with straight edges like that, or with a wide or narrow bottom like that. The third type, the same way, by controlling the web location and the edges here. You can make it with a wide edge or narrow edge like that. And one more option for here for the top width of the rib and the bottom width of the rib, and we will check that during the demonstration. One more type, which is the saddle with lifting lugs. This type actually we created based on one of our clients' requirements in USA. They are a heat exchanger manufacturer, and they asked us to add this type because they usually used it to avoid welding lifting lugs on the shell or the shell body of the heat exchanger by lifting the heat exchanger from the lifting points on the saddle. Some other options on the saddle, like making a saddle with a cut. In some specs, you may need to make a cut on the saddle, saddle web, because you have not enough area here to tight the anchor bolt. So some specs include this cut, and SEG give you the ability to make a cut to control the bottom and top and width and the length of this cut on the web. You can make the holes as straight holes like that, or make it as a slot hole like that option, or make it without any holes. So SEG will automatically detect that this saddle without any holes if you make the value of the hole as 0 or the number of holes as 0. So you can make this saddle without any holes. In some specs, the sliding saddle not include any holes. It's just fixing by fixation from the two sides and a Teflon below the base plate. So the sliding saddle may not include any holes. You can control the direction of the pattern direction of the holes. You can make it on the short direction, or you can make it on the long direction. the number of reps, you can make it up to 9 reps for the first pipe, or 7 reps on the second, third, and the fourth pipes. Okay, now let's come back to our model here and select this saddle. And from this list, you will find the 12 cases. Here, that's the first case, case 1. The middle case, left rib case, and right rib web case. So let's select the web to be at the middle, and let's define the dimensions of the saddle. So the contact angle 120, and the height of the saddle is 3 meters. The web thickness 30 millimeters. And from here, this option will give you the ability to control the bottom width of the saddle. So as we discussed here.
Mr. Ahmed?
Yes.
One question. Can we add the double pads as well? Because UL142 asks for the double pads, like this reinforcing pad. In this one, we have only one pad. So as per UL142 horizontal tanks, we need double pads. One. You are aware about this configuration?
Double pads on I cannot understand what do you like to say.
This wear plate.
Yes.
This contact angle is showing 120, and we use one more plate attached to the shell at the same location with angle of 140 or 145 degree based on UL142 code. So we will have 2 pads except instead of 1 pad. So can we do this in this software? We have any option?
Okay.
We can attach.
As I understand, after adding this wear plate, you would like to add another wear
Yes.
as extend.
Yes, it will be extended.
Okay.
Yes.
Okay. In the saddle itself, it's not included, but you can use another attachment, which is external bed. There is another part on the attachment.
So we can introduce one part between the shell and the saddle.
Again, please.
We will introduce one additional wear plate between the saddle and the shell. So this will be attached to the shell as an attachment, external attachment.
Yes, but okay.
Can I show?
Let me make a sketch to understand this. That's the shell, okay? And you have here the let's say that's the wear plate here, okay?
Yes.
Of the saddle.
Yes.
You mean you have another? Sorry, you mean that you have another wear plate here, or another wear plate? Sorry, or another wear plate. That's
yes. Double wear plate. Then you will put yes.
Mm-hmm. No.
Okay.
This option is not available by adding a double wear plate. But if you would like to add something like that, it's not an issue. Kindly raise your request to our technical team, and inshallah our technical team will provide it and submit it on the next release. Inshallah.
Okay. For more clarity, can I show a little bit for more clarity?
Kindly share your screen.
This you can see now?
Yes.
Okay. This plate. This is a UL142 requirement to use the double wear plate.
Mm-hmm.
So this I am asking. In this view, you can see this as double plate.
Yes, I see. So we can make it, but around that. But let's try it on the second saddle. Let's make the first saddle with one wear plate.
Okay.
Let's try to make it on the second saddle with a double rib edge.
Okay.
Now you can see my screen.
Yes.
Okay. So from here, let's define the dimensions of this saddle. We have an outer ribs, so let's define the top width of the saddle. So you can control the top width of the rib and the bottom width. So you can make it as here. So you can so you can control the bottom width and the top width of the web, like here. Sorry. Here you have different widths for the web, so you can control that by changing those dimensions, the top width and the bottom width of the rib. Here's the rib thickness, and let's add intermediate ribs and define the spacing between them. Another intermediate ribs and define the spacing between them. And from here, let's add a weir plate. Define the contact angle of this weir plate and define the width. Find the thickness. Okay, and from here, let's edit the fillet. And for the base plate length, let's define the length of the base plate and the width, the thickness of the base plate, and the whole diameter. Let's make it millimeters, and the offset from the short edge. Okay, and the offset from the long edge. And it's not a sliding saddle; it's a fixed saddle. So let's define the number of holes per row, and we have 2 rows of holes. Like if we come back here, and from here, if you would like to make a single row, okay, you will remove this checkbox. And if you would like to add a second row, you have 2 rows of holes like that. You will select second row, and the number of holes per row, it's 3 holes per row. So we will get 2 holes here and 1 hole at the middle. That's the number of holes per row. Now let's define the location of this saddle. Okay, the location is 2742, and let's click on save. Now let's click on start assembly to start generating the first saddle. As you can see, the rendering of the assembly takes place on Autodesk Inventor. That's why, because of we select an option to make a rendering for elements during creation, that will give you the ability to render the element during creation. Let's discuss this option again from the setting here. If you select child preview, that will give you the ability to make a render for element during creation. If not, that will be generated on behind. After that, you will find it appear in one time on the final assembly of the vessel. Now let's try to make the second saddle with 2 weir plates. Okay, let's add the sliding saddle. From here, let's select a saddle and make it right. Saddle. And from here, let's make it looks like the left saddle, and let's click on add. Now we have another saddle with the same dimensions of the first saddle. We need to make a change on the location of this saddle and make the holes as a slot holes. So the location will be like that, and the holes we will make it as a slot hole. So from here, let's select sliding and make it the slot length at the 30 millimeters and click on save. Now let's create this saddle as it is right now, and after that, let's add another weir plate below this one. Okay, now we have the second saddle with slot holes like that. Now let's try to add a weir plate under that one. So from here, let's select the can, and from elements, let's add an external attachment, and from here, let's add an external bed. So let's add it as a right saddle bed. Okay. From here, let's define the length of this one. So to get the length, we can make you can define it as a length, and if you would like to calculate it as from the angle, if you have an angle, we have a calculator here from the setting. Let's define the inside diameter of the mid diameter of the rebed. So if we have this vessel with 400 millimeters, and that's the thickness, and the rebed, let's say it's 14 millimeters, so that's sorry, so that's the double thickness of the weir plate. So that's the outside them. No, it is this value. So that's the mid diameter of the weir plate. If we I would like to make it as a sketch here to show you what I mean. Here we have that's the vessel outside diameter, which is 4 meters plus that's the thickness. Here we have 4 meters plus double thickness, so that's the outside diameter of the shell. And here we have an arc like that. This arc defines the mid diameter of the weir plate, the extra weir plate. Okay. And we need to get the let's define all of that as construction lines. We would like to define it as 160 degrees. That will be the middle of that value. Okay, so to calculate that diameter, we need to define the half of the thickness, which is, let's say, 14 by half. So that will be the diameter of the midpoint of the extra weir plate. So let's get this value, which is 4,250. And the arc length, we need to calculate it, and the angle is 160. So the arc length will be like that. Okay, that's the arc length based on this angle. So we can take this value directly. We can take this value directly and paste it here on the length. Okay, so let's take that one like that. Close this one and make paste for this value. And if we calculate it, get it from here from the inventor by getting the arc length, we should get the same value, which is 5934, okay, which is the same value here, by getting it from this calculator, which is give us the arc length or the angle. For example, if you have this value for the diameter, and that's the arc length, you have 6 meters arc length. If you would like to get the angle for this length, you can get it from here. Okay, so let's define it as 6 meters. Okay, and the width should be greater than the width of the saddle. Let's close this model. I hope this point clear how I calculated the arc length. Okay. Hello.
Yes, it's clear.
Okay. Okay. The width of the weir blade, we need to make it wider than this value. So if we, I think we had it as 760. Okay, so let's make it 900. So from here, let's define the width to be 900, and the thickness as we make as 14, and the fillet will be 50, and the location will be the same saddle location, which is 9942, and the orientation will be on 100 and
How fillet will be 50?
Again?
Fillet will be 50? How?
The fillet at the edges, like that fillet here.
Ah, okay. Radius.
Yes, the fillet.
Okay.
Okay. Now let's add this one, and let's create the this saddle, this wear plate. Sorry, I flipped the values. Sorry, so the length instead of the width. So you can figure that it's become like that. So let's come back again and make that. And let's click on save and start to update the wear plate dimensions. Okay, now you can figure that we have another wear plate, but you will figure that we have a clash between those pads. If we make analyze interference between that one and that one, you can figure that you have an interference between them, because the pad of the rebad of the saddle takes the outside diameter of the shell, not the extra rebad outside diameter. So how we can deal with that from Autodesk Inventor itself, because we cannot deal it with from SEG. So how to deal with that? By double clicking on this wear plate. So we come to the level of detail of this wear plate, and from the parameters we will modify the shell outside diameter. So let's add plus 14 here for the shell, and by that way you can figure that the rebad comes over the let's decrease the thickness of the rebad. Sorry, so we need to decrease the thickness of the rebad because the thickness of this rebad changed. It's not now 30 millimeters, so we need to decrease this value by 14 millimeters, which is the same value we increase it on the shell. Now, if we finish this, you can figure that you have those two rebads. We can change the color of this rebad to red, for example. Let's make it smooth red. And let's close this one. So we have two rebads that way.
Okay, good. How can you go back to the repad tab? How you select the location of this repad? It is exactly at the center of the web or the center of the saddle.
I give it the same location of the saddle. Here, if you take a look to this saddle takes a location, that value, 9942. Okay. If you come back to the rebad, it takes the same location and the same orientation. If you make that at 0 degree, this rebad will be at the top, not at the bottom.
Okay.
Okay. So
now the height of the rib and web changed now for the right saddle?
No, it's not a change. It's the thickness of the wear blade only. I changed it.
But the height should be changed a little bit around thickness.
No, I keep the thickness 30 millimeters. Both saddles thickness are 30 millimeters. The summation of them.
I mean the foundation of the saddle in the same level, right?
Again,
base plate of the saddle in the same level, right?
Yes.
So if you add another wear plate, that means the height of the right saddle would be decreased.
No, what I did is making the both of rebads. Okay. Now one bad, the single bad thickness was 30 millimeters. Okay. But after adding two wear plates, I make one of them 14 millimeters. Okay, and the second one will be 16. So the summation of them still the same, 30 millimeters.
Okay, I mean, if we have different wheel blade thickness more than the left saddle, in this case, the whip and rim will be changed automatically.
طب اقولها ازاي؟ But in that case, we didn't make a change for the.
I know. I mean, if we add another wheel blade, like Mr. Wakar asking, with the same parent of the existing wheel blade. Yeah, we add more thickness. In this case, the rib and the whip will be decreasing to maintain the level of the base blade.
They will not change because on the beginning
Actually,
I takes both thicknesses on the first rebad.
okay,
Here
Mr.
I have a rebad here with 14 millimeters, okay, and another bad with 16 millimeters. So
Mr. Ahmed,
during adding the information here, I add the wear plate thickness as both of thicknesses. Both.
If we add 30 millimeter plus 14 millimeter.
So you will add here 44, not 30.
Treat it as a sliding blade. Same case of sliding blade. In sliding blade, there is two different dimensions for right side and the left side.
They will change. If you make this thickness as a 44 millimeters, they will not be the same. The ribs height and whips will be changed. They will not be the same.
Yes, that's why.
Because the thickness here of the wear blade not become 44, but in that case it's only 30.
Mr. Ahmed, how you manage? You go to the manage toolbar and then you select edit this thing, make it 16 and 14. Can you go again to this toolbar?
No, it's not a toolbar. From here, from the SEG tree, you will need to select the element from the tree. If you would like to edit as a shell, just select the icon of the shell from here, and you will get this form. So you can modify, change the type, or change the dimension. For the saddle, when you select the saddle from the tree, you will get the form on the drawing area on the middle.
No, you go to the manage box. There was some manage box, and you change the point because before they were clashing.
Okay, you are talking about here on Autodesk Inventor.
Yes,
as mentioned, this change you cannot make it, or this type is not supported in SEG. So you can make this modification from Autodesk Inventor itself. So SEG help you to create it, but something like that you will need to make some manual modifications. Here for this wear blade, when we select to double click on it and go to the level, the edit level of this part, from the manage tab, you will get the parameters of this wear blade. From here, I changed the outside diameter of the thickness of the shell by increasing the thickness of the shell plus the extra rebad thickness here. Okay, and the wear blade thickness, I decrease the thickness of this rebad from the thickness of the whip.
Okay, what Mr. Khalid was saying, he was saying, and we will make 30 as 44, right?
Okay, so let's change it. Let's change
Mr.
it.
Ahmed, I have a question here, please.
Okay,
we changed the parameters.
Would you mind to make this modification first?
Okay.
Okay, so let's increase the second saddle. The second saddle thickness to be 60. Okay, the both thicknesses will be 60, 30 and 30. Okay, 30 millimeters for the extra reband and 30 millimeters for the saddle reband. So we need to add both thicknesses here. Okay, and click on save. And let's come back to the rebad here and define the thickness of this rebad as 30 millimeters. Is that okay?
Okay.
Okay. Now let's start the assembly. Here you can figure that the web cut changed and the outside ribs values changed to suit the new thickness of the wear plate. Okay, and here the thickness of the extra wear plate will be 30 millimeters. If we take a look from the other side, you can figure that the second saddle is not the same as the first saddle. You can figure that the second saddle not the same with the first saddle. There is a change.
But at the same level, right?
Yes, it's the same level because they are the same projection or the same height.
Okay. Yes. Okay.
Look to the saddle. I have a parameter here for the height of the saddle, which is the distance from the center of the vessel to the base plate bottom surface. That's the height. If you have a change on that height, you will get it on the 3D model, but they are the same, 3 meters. Okay. Now we still facing this issue after modifying the thickness and update the model. This wear plate thickness is still 60 millimeters. If we goes inside here, you can figure that it's intersect with the main vessel, for the extra rebed. Okay, so we need to go inside that one and manage the parameters here. If you take a look, that's the shell thickness, and we need to increase the shell thickness by the thickness of the extra rebed and decrease the thickness of this rebed by the same value of the rebed. So if we make an update for that, you can figure that now the extra bed and the internal bed, they are flushed. Now let's click on finish. Like that. But you still have one more point. This rebed thickness will appear on the bill of material with 60 millimeter thickness, not 30. We modify it manually. Okay, but if you open SEG bill of material here, so something like that, you will need to modify it in your drawing or in your exported model, because as mentioned, this type is not supported, which is double rebed. So if you pick the rebed or wear plate here, you have a wear plate here, another wear plate, another here. That's a 60 millimeters thickness. Okay, so that value you will need to modify it manually from in your drawing. Okay, because we defined it here as 60 millimeters, but make the modification manually here on the 3D model.
But it is not, I mean, maybe
we make some workaround to get the same. Sorry?
Yes, I was about to ask that maybe in the future updation you can consider and update in the SEG software as well.
Yes. Yes, if you raised your question to our technical team, or your request to our technical team, inshallah, we can do
because
it.
UL 142 tanks are very common, and
actually, that's the first time a client asked us about something like that.
Because it is very common, UL 142. We have my next question is about the slope of this vessel, because this is very repetitive job in Saudi Arabia with Saudi Aramco. We have slope tanks.
As mentioned, the SEG include 3 different positions for the vessel: vertical vessel, okay, horizontal vessels, and the tilted vessels.
No, slope with this same configuration, because you show it was tilted, but it was supported, fully bottom supported. But in this saddle supported, one saddle is higher and other saddle is lower level.
That means that this vessel is tilted vessel. Okay, I will show you something. It's not a horizontal vessel in that case. It's a tilted vessel. If you have a saddle with a different height from another saddle, that means it's not a horizontal. It's not so it's a tilted vessel. So you can control. Here, if you go to our channel, you will find a lot of videos. Some of them regarding the tilted vessels. Here, for example, here. Let's open that one. It's a quick tutorial. So, yes. Yeah. Okay, here on this video, here we generate, if you take a look here, we will select an option for a sloped vessel or a tilted vessel,
okay,
horizontal
yes,
or vertical, and you can define the tilted angle. Here we
okay,
make this tilted angle as 44 degrees. After that, you can define if you add a saddle, for example, you have a reference point, so you can define the height and the location. Automatically, SEG, if you define the location from the reference point, it will calculate the actual location on the tilted body. The same for nozzles and something like that. You can figure that from this view, it's a tilted vessel with different saddle heights. So actually, if you have a nozzle, if you have a long vessel, so this with, let's say, a half tilted angle, that will accumulate a big difference for nozzles projection or
yes.
So by using this type of tilted vessels, you can get and calculate that automatically. Here, that's as a drawing. If we make the drawing by adding, so the location will be calculated from the reference point, which is the tan line at the middle, like that. So the option of tilted vessels available in SEG software.
Okay, there are two lines. One is the true
the original center line, original center line, and the tilted, which will be tilted. The original center line will be tilted.
Yes.
But the horizontal center line still be the same as from the reference point as the tan line of the head.
Okay. So if I will have to mark the location on the true longitudinal line, which is tilted, okay. So because in the workshop, when you prepare the shell and you will have to take the measurement, so you will move along the shell, which is in the tilted direction. So in that way, is it also possible you can show the reference point of nozzle from that in that direction, slope?
In that case, you should start your vessel from the beginning as a tilted vessel, because in that case you will need to add a tilted saddle, not a saddle.
Okay.
If we come back here, if you select the shell course, and from elements, you can figure that you have a saddle. This saddle, you can use it on horizontal vessels, and saddles. But you will find a tilted saddle. This tilted saddle only used for the tilted vessels. Okay. So you should, from the beginning, select the option of sloped vessel and define the sloped angle. Actually, you will find a lot of videos here on our channel, so you can check them, and you will know how to make something like that for the tilted vessels. Okay. As mentioned here, for the second saddle, wear plate thickness, here it's defined here 60, so it will appear on the bill of material as 60 millimeter. So you will need to modify that manually on the bill of material after exporting it to your drawing. Inshallah, after providing us with your request, inshallah, our technical team will work on that to make it available on the next releases, inshallah.
Okay.
Okay. Now let's add a lifting tranion, and before that, let's discuss some options for the lifting shapes or configurations which they are available in SEG.
Mr. Ahmed, before lifting the point of saddles.
Sorry. Yes.
I have a question regarding the saddles.
Yes.
If we go back to the Windows settings. No, it's the modeling.
Yeah.
Regarding the number of intermediate trips. Actually, we have a lot of cases that we have a lot of 6 or 7 intermediate trips in the one settings. So I see here in the program that you have only 2 intermediate trips available.
No, if you take a look here, you can add mid-rip and three levels of intermediate reps. So totally you can add nine reps in this type of saddle. If you would like to add more
yes, more intermediate
kindly raise your request to our technical team, and inshallah we can provide that in the next release.
Okay.
Can we continue?
Hello? Yeah, I was asking about the parameters changing in the model of inventors. Yeah. We changed the parameters in inventor manually, but not in SEG. So can you take us what the consideration to take in mind in software in order not to when we update the parameters in SEG, there is no conflict in the inventor model.
Okay. Here, if you can figure that there are some parameters SEG can control them. Like for the wear plate, for example, here that's the contact angle of the wear plate, the width of the wear plate, the thickness, fillet, and material of the wear plate. So all of that will be reflected to this element. If we open this wear plate in a separate form, you can figure that that's the material which send from SEG to Autodesk Inventor. The same for the parameters. If you open the Manage tab, you can figure that the location, the orientation, wear blade thickness, wear blade width, fillet, all of that. Those are parameters sent from SEG to Autodesk. And there are some parameters related to the main element, which is the shell. So here that's the shell inside diameter and the shell thickness. And some other parameters calculated here from some equations send from SEG directly to Autodesk Inventor, and some other parameters calculated from Autodesk Inventor and send back again to SEG. Okay, so it's a mix of parameters from here to there. Now,
so the consideration
about
yeah.
Go ahead.
The consideration I must take in my mind to avoid when I want to update the parameters in SEG, it will not delete the whole thing I built it in Inventor here. Do you get my point?
Yes, but it will not delete all of things that you did. But you should take care that you have some parameters. Those parameters are generated by SEG. Okay, so after during making a modification, SEG will send the commands or send those new values to those parameters here. If you would like, for example, if you would like to make a hole as a tab hole for weld, so let's make a plane here. Let's make a work plane and create sketch here, and you would like to make hole like that, and this, let's make it as a center line, and now let's define the orientation of this line. So you can define that as from the parameters which send from Autodesk Inventor, like the wear blade contact angle. So you can get this value. You can divide it by 2. Okay. So if you click yes, for example, you will get the end point of this wear blade. So you want to make this hole with less than 2 degrees or 4 degrees, for example, from here. Okay. Find the length of that one to be the ID of the shell, for example. Find the whole diameter of this tab to 10 millimeters. And let's make revolve for that one around the axe and make it as a cut. So you can figure that you create a new hole here. Anytime you will change the value of the contact angle, for example, if we change it manually, let's make it 150 and make update. You can figure that the hole will be moved with it because you make this value related to the contact angle. Okay, so you can consider the parameters of the model in your modification. And if you would like to make it without any consideration, like make it on a constant value like 60 degrees. So when you make the change manually, that will not reflect on your new feature. Okay, so it depends up on you. How you, if you would like to use the parameters of the model, you can use it. And if you would like to create your own parameters, like hole diameter, for example, let's create this value as 50 millimeters. You can create your parameters and use it in your model. So from here, let's define this value as hole diameter. So by that way, you can, during modification on Autodesk Inventor, you should have enough experience with Autodesk Inventor to deal with the parameters without missing anything or using the old parameters and adding your new parameters if you would like to do that. I hope now.
Yeah. But if I want to update the model in SEG and run assembly,
yes,
can the parameters I changed here in the change parameters of configuration in Inventor when were reflected also?
No, no. As mentioned, the parameters here is stored. They are stored on the SEG file. Okay. Some other parameters like the circumference length of the blade after, like if we come back here and get the sheet metal development. Sorry, if we create the sheet metal development for that. Here, SEG give a command to Autodesk Inventor to get the flat pattern for the blade. Okay. After that, SEG will get this value and store it on the file to use it to make it appear here. Okay, if we, which is that value. This value is a calculated value from Autodesk Inventor and it's reflected to SEG. So those are the parameters that you can get it from Autodesk Inventor, not the sended parameters from SEG. So if you have a parameter here, you will need to send it to Autodesk Inventor. If you change it in Autodesk Inventor, it will not change it. Okay.
So when I run, I need to not run the assembly. When I click save in the save button of this node, does the parameters will create from the start, or it will keep the changing?
Okay. It's based on your changes. For example, here you already create the part. You already create the part and make a modification not related to the main configuration. You just make a hole here. Okay, this hole not related to the main configuration. If you change the wear blade contact angle or the wear blade width or any other thing, the thickness, the configuration, the main configuration will be changed based on the new parameters. Okay.
What the height?
The part will not generate it from scratch. If it's created,
yeah.
If you already have this part created onto disk inventor, SEG will send the new parameters, the new values for the parameters to this part again to update it. Okay. So if you have extra features you added like this hole or any other features, it will be related to what you are did. As mentioned, if you make this hole based on some parameters, those parameters, some of them related to SEG parameters, so they will be affected by the values of the SEG. If not, they will not change. They will be a constant value. I hope you get my point.
Yeah. Thanks.
So during making a modification on SEG parts, you should have experience to do that without making. I mean, with experience with Autodesk Inventor. You know how you make features, how to make parameters, how to make a flexible sketches. Okay, all of that you should have some experience if you would like to make a modification. But if not, it's okay. You will use the SEG parts as they are. Okay, now let's add some nozzles to this model. Let's start with the let's add a trunnion, lifting trunnions. So from here, let's select the first can and from elements. Okay, before discussing the trunnion, let's discuss some of the available lifting parts for the vertical, horizontal vessels and horizontal vessels. Here you will find on this image some of the available types of lifting lugs and trunnions. Some of them suits the horizontal vessels, small sizes, mid sizes, and larger sizes. Some of them suits the vertical vessels. And on the next slides, we will discuss those parts on detail. The first type, which is lifting lug type 1, suits the horizontal vessels or vertical vessels, but this lifting lug direction will be on the longitudinal direction like that. You can control the whole position, so that will give you a flexibility on the configuration of this lifting lug by controlling the dimension. That will change the configuration of this lifting lug. You can add, by the way, you can control adding a wear blade and cooler, lifting cooler. The same configuration, but in that case, you can make it on circumference direction, not the longitudinal direction. If you take a look to the previous one, the direction of the lifting lug is on the longitudinal direction, but for that one, it's in the circumference direction like that. And the same option here, you can control the value of the whole offset from the edge, so you can change the configuration of this lifting lug. Another type of lifting lug, which lifting lug type 3, you can use this type for the mid-size vessels. This type includes a rebad, a stiffening grip, the lifting lug itself, and lifting cooler. So you can select the option of adding a wear blade or a cooler for this lifting lug. Another type for horizontal vessels, but for large sizes, you can use it. Actually, we create this type based on one of our clients' request. Here you can define the dimensions as per the image on the right-hand side. Another common type for vertical vessels, which is this type of lifting lug. You can control the lifting lug in the configuration to make it with a fillet with an end fillet like that, or with a chamfer. You can control the end of the lifting lug. You can make it without any cut at the end. You can make this cut with sharp corners or with a fillet corners like that. You can add a wear plate or a cooler. You can add a stiffening rib to this lifting lug at the top. Another type of lifting lugs suits the small sizes for heat exchanger bonnet or a channel or small vessels. On the longitudinal direction and circumference direction, you can control the end fillet or make it with a chamfer. The same for circumference direction. Another type for lifting lugs with two stiffening ribs like that suits the mid size of horizontal vessels. Another type for lifting lugs, which is cross type. This type gives you the ability to lift your equipment from a single point. As you can see, the lifting lugs are crossed with each other in one point like that. Another type for lifting lugs, this type actually we generated based on one of our clients' requirements. So by sending us this spec, we used it to make a standard sizes and give an option. If you would like to define all of those items manually, you can do that. After selecting this part, you can modify the dimensions as per your mechanical calculations. Another type for the lifting tranions, and you can figure that you have some options here to add an end blade. So it's an option to add end blade. In the second case here, you can figure that no end blade. Okay. For the external stiffening ring, you have an option to add a single stiffening ring or double stiffening external stiffening rings. The same for internal rings. Here in the first case, no internal rings. In that case, you have a single internal ring or a double internal stiffening ring. Another type of lifting lugs suits the vertical and horizontal vessels. You can make the neck of this lifting lug from a pipe or from plate. Now let's go back to our project and let's add a lifting tranion. So from here, let's add a tranion type 1. And from here, you can figure that you can make this tranion as a neck from plate or make it from pipe. So in our case, let's make the neck of this tranion as a pipe. So let's select the size as 24. The scalable is 40. And from here, define the projection of this tranion as 300 millimeters. And the location will be 942. And the orientation will be 90 degrees. And from here, let's add a rebad. So let's define the rebad width, the rebad thickness, and define the rebad material. Let's add outer rings. So the outer ring diameter and the outer ring thickness, and the offset of this, the first ring, let's make it at 0. And from here, let's add a second ring and make the spacing between rings, which is dimension B. Let's define it as 80 millimeters. And let's add a single ring at the inside. So from here, let's add an inner ring, the inside diameter of the inner ring, the thickness, and the offset of this ring from the edge. And let's remove a second ring. We will add single ring only. And from here, let's make the quantity of that to be 2 lifting lugs, 2 tranions. Now let's create the assembly. Now we have the first tranion. Let's add the second tranion to this vessel. So from here, let's select can 1, and from elements, let's add tranion type 1. And to avoid repeating data entry again, let's select same as and select the tranion from here and click on add. Now we have the second tranion. We will need to change the location of this one. So from here, let's change the location of this tranion like that, and click on start assembly to generate the second one. Okay, now as you can see, we have the final model for the main elements, saddles and tranion. Now we will proceed creating the nozzles of this vessel. So from here, let's select the first head, and from elements, let's add a nozzle with external projection. If you would like to add a nozzle with internal and external projection, you will need to select this type, which is head nozzle type B. But in our case, we will add a nozzle with external projection. Okay, and click on save. Now, if you select this nozzle, you will find different types of nozzles available here, like nozzle with a neck from pipe, or a nozzle from blade, or a long weld neck nozzle, self-reinforcement long weld neck. So if we take a look to the available types of nozzles here in SEG, you will find some types available for shell nozzles or head nozzles or cone nozzles. The most available types, you will find it on the shell, more than 23 types of nozzles. For example, if you would like to make a nozzle and the neck of this nozzle from pipe, you will find a type of nozzles that give you this ability. Another type, the neck of the nozzle from blade, so rolled blade. Another type from long weld neck, as a long weld neck nozzle according to ASME or the European codes. Self-reinforcement long weld neck nozzle. Forged hub with lips. Integral hub or integral hub with lips. Rectangular opening and oval opening. Those are some of the most common shapes. Some of them you will find, all of them you will find them on shell nozzles, but on head nozzles, not all types are available. So on head, you will not find the rectangular or oval nozzles. So let's come back again to our model here and select the type of nozzles which suits our case, which is self-reinforcement standard forged hub. In this type, you will get the same pipe dimensions at the end. So it suits a standard pipe. You can weld it to a standard pipe. So you can define the outside diameter, the size of the pipe, the schedule of the pipe, and define the hub dimensions and the insert bed dimensions. Okay, here in that case, let's select this nozzle as a 6 inches nozzle, and define the thickness of this nozzle to be 40 as a schedule 40. Here you will find the thickness of this nozzle, and from here you can define the height, the thickness and the bevel height. So the bevel height will be calculated as the hub thickness negative the end thickness. So it will be negative 7.1. That's in case the bevel angle is 45 degrees. So here that's the thickness or the bevel height, sorry. So let's add the bevel height here and the offset of the nozzle. Let's make it 1200. The orientation will be 180 degrees. Okay, and for the projection, let's calculate it by another way automatically from SEG, but let's complete the data entry here. That's let's make the width of this nozzle, the width of the web as 100 millimeters, or let's increase it like that, and the thickness shall be the head thickness, which is 60 millimeters. We will give it the same thickness of the head. If you would like to make this insert bed with a greater thickness or more than the head, you can define it directly from here. Let's decrease this value a little bit, and from here, let's define the nozzle service as outlet, something like that, and click on save. Okay, now if we add a flange to this nozzle, from here let's add a flange. You will find an option to add a standard flanges and design flanges. The design flanges, you can use them in case if you have a non-standard flange, you would like to define it, like in heat exchanger. So you will find a huge list of design flanges on that main element. Now let's add a standard flange, which is in 5B flange. Click enter. Now from here, let's select a Wildeneck RTJ flange with a ring joint according to ASME B16.5, and select the rating to be 900, and the size will be the same size of the nozzle, which is 6 inches, and the schedule the same schedule. And from here you can define the material, and if you would like to rotate the flange, if you keep it 0, the standard orientation will be still the same, will be aligned. But if you would like to rotate the flange a little bit, you can control the orientation of the flange. From here, let's come back to the nozzle again, and from the calculator, if you open this form, from here, if you can define the projection of the nozzle from the tan line of this, or the seam line, sorry, from the seam line of this element to the facing of the flange, if you have a flange. Here you can figure that this form detects that you have a flange connected to this nozzle, and that's the flange height. And if you have an elbow, it will be to the center of the elbow. SEG will detect that and calculate the diameter of this elbow to decrease it from the value of the projection. Now, if we define the projection of this nozzle to be 2,200, and let's click on calculate. If we click calculate, SEG will start creating a sketch to calculate the required projection here, and here SEG gives us the value of the projection of the pipe from the facing the pipe, the straight pipe here. If you take an image, yes, you can figure that you will need to define the projection from the seam line, which is that value. Okay, and the calculated value here, it's the projection here. So that's the calculated value. This calculated value will be reflected back on the projection here on the the blue form, we come back here. You have this projection. So this value, will be reflected from here to there if you click on save. Okay, so you can use this form to calculate the actual projection of the pipe after adding a flange and after decreasing the arc height here at this point. So let's come back to SEG and decrease this value a little bit and click on calculate. Okay, and click on save. Now you can figure that the projection of the pipe now decreased. If we click on start assembly, now we have this forged hub like that here on this head. Now let's, if you would like to add another pipe between the flange and the forged hub, you would like to make an extra element between this forged hub and the flange. So if you come back here and select the external connection, and from elements, let's add a pipe. So it's 5B pipe. And from here, let's define this pipe as the same pipe dimensions, 6 inches, and I think it was 40. Yes, 40 scalable 40, and the length will be 200 millimeters. And click on save. Okay. Now, if we generate the assembly from the tree, you can detect that the pipe will come after the flange, not previous the flange. Okay. Now you can see that the pipe comes after the flange, not previous. We need to move this pipe before the flange. So this pipe will be directly connected to the forged hub, after that the flange. So how we can do that? By using the move commands. So from here, if you select this pipe and right click, and from here you can select move and make it move before. Okay, so from this list you will find that you can move it before this flange. So if you select and move, you can figure that the color of the element will be changed to blue. That means the UCS of the assembly, which makes the arrangement of elements, need to be updated. Okay, so when you click on start and come back to the model, the assembly will be updated like that. So the pipe will come before the forged hub, after that the flange. Now one more thing regarding the nozzle projection. Here when we change the projection is still the same here. Okay, but if you take a look to the nozzle table, if we open the nozzle table, you can figure that the projection still 2000, but we increase it by 2200. So if we make a quick drawing, fast drawing to check that here, to show you what I would like to say, if we add this vessel, like that, we have here this reference line. If we measure to the facing of the flange, we increase it by 200 millimeters, which they are the value of this pipe. So we need to reflect it to the calculated projection. So from here, if you add this value like that, you can modify this value before adding the nozzle or the pipe. So let's close this form and let's make this flange, make it directly connected to the hub. So let's make it move before the pipe. Okay, and come back here. And if you open the calculator, you can define the new value like that, and add the extra length of the pipe, which is 200 millimeters, because we have 200 millimeters here. So you can add the extra length here. And if you click on calculate, now you will get the correct value, and the projection on the nozzle table updated to 2200. Now let's come get back this pipe after the flange, and let's click start the assembly. Okay, now we have this nozzle, and let's add another attachment to this head. So let's select the left head, and from elements, let's add a support pipe. And from supports, you can add a support pipe. By the way, we generate this type, which is support channel, based on one of our clients in Australia. They have another code for the pipe sizes. Okay, and based on their requirements, we generate that according to Australian codes. Here, let's select this type of pipe, and from here, let's select the size to be 10 inches with 60 as a schedule, and let's define the projection as 100, and the orientation will be at 0, and the projection will be 150. And let's add a reband, define the reband width and thickness. Let's add end plate, define the end plate dimensions, thickness, and the hole diameter, and the hole offset, and the material of this support. By the way, you can add stiffening ribs if you would like to add ribs like that. Now let's generate this part. Okay, now we have this support on the head, this clip support on the left head, like that. Now let's add some other nozzles and manway to the second head. So from here, let's select the right head, and from elements, let's add manway. So it's M2. And from here, let's select self-reinforcement standard forged hub, like that, and define the dimensions of this forged hub. It's 24 inches with 80 as a schedule, and define the offset to be 500 millimeters, and the orientation to be 180 degrees. Okay, and from here, let's define the hub height, the hub thickness, and the bevel height, which should be the hub thickness negative this value. So if you decrease the value of the thickness from here, you will get that value if the bevel angle is 45 degrees. Okay, here that's the width of the insert band. and the thickness of the head is 60 millimeters, and the fillet at the bottom and top. That one is plan A. Okay, and let's click on save. Now to let's add another flange as a designed flange, which is M2 flange. And from here, let's select weld neck RTG according to SMAB 16.5. Select the rating and the size of the flange, and from here select the same schedule of the pipe and click on save. Now if we come back to the nozzle, you can define the projection in a correct way from the seam line to the flange facing. So let's define the projection like that and click on calculate. In that case, SEG will start creating a sketch to calculate the right value of the nozzle, and let's click on save. Now if we click on start assembly, we will generate this forged hub for nozzle M2.
Mr. Ahmed?
Yes.
Do we have any other standards for flanges? Like we have, I just see the ASME flanges. Do we have any option for DIN flanges, PN16, PN10 ratings?
Let's take a look to flanges. If we select this flange, for example, you can find that those are the standard flanges, the list of standard flanges. As mentioned,
can you go down? Can you scroll down?
Yes, I will scroll down, but let's discuss this point first. Here you have a standard flanges and the designed flanges. As mentioned, the designed flanges, it's not a standard configuration. Usually we can use it on heat exchangers, and if you have a vessel with a diameter not suits the standard size, you can use the designed flanges. The same for flanges. Here for the standard flanges, if you take a look, you can figure that you have a long weld neck raised face, long weld neck RTG, slip-on threaded flange, lap joint. Those are related to ASME, like 16.47. Some of them related to the European codes, like CN, and another types for long weld neck, but to another code. For the API flanges for tanks, those are the available types, and some of other flanges not standard. You can define them, but actually for the non-standard flanges, you may need to use the designed flanges from this tab. Let's add the designed flange. After that, we can delete it. Show you some of that. Here for the integral weld neck raised face. Here you can figure that the facing of this flange with a positive raised face here. That one with a negative raised face. So the raised face is a groove here. And another with integral flat face. So you will find a list of flanges here suits the requirements of to design to make a design for non-standard flanges. Let's delete this one, and let's come back to the flange to nozzle M2. Here we have this nozzle with RTJ facing. Now let's add RTJ gasket body cover and make it as a manway. Now from let's select the external connection point for the nozzle. So if we take an image from that, you can figure that here you have this nozzle, which is M2, and this nozzle include an external connection. So from this external connection, you can add other elements. Here we add a flange. You can add another elements to this part after the external connection. Okay, so from here we can add a gasket, another cover, like what we did here on this nozzle. From the nozzle external connection, we add a pipe, add another flange. You can make a list of connections here. For the nozzles with internal and external projection, you will find another connection point to the internal connection, and we will discuss that on another point, inshallah, another nozzle. So from external here, let's add a gasket. So M2 gasket. And from here, let's select a gasket suits this one, which is RTJ gaskets, and select the rating and the size of the flange. Define the material and click Save. Let's add a cover on blind flange. M2. And from here, you will find a list of standard blind flanges. So let's select RTJ blind according to SMB 16.5. Select the rating and size. One more option we will make it here, which is flipped, but let's keep it without selecting to show you the meaning of this option. Here, if you click simply, the RTJ gasket shall be created. After that, the blind flange. Here, as you can see, the facing of the cover comes out, not to the facing of the gasket. To flip the direction of this blind flange, like what we did on the head, as you can remember, this head and that one, they are identical, but one of them with a flipped option. If we select this, the first head, this option is not selected, which is flipped direction. But on the right head, if we select the right head, you can figure that we selected this option to flip the direction of the head. The same thing, we will do it with the flange. So by selecting this cover, we will select flip option and click on Save to make the facing of this blind flange to the direction of the gasket. Okay, now we have this blind and the gasket on the facing of the raised face, or the RTJ facing of this blind. Now let's add some other attachments like hand grip for this cover, add manway davit, add stud bolts. So let's select the blind, and from elements you can figure that you have some attachments to this blind, like if you would like to add a nozzle to this blind, and this nozzle with external projection, or adding a nozzle with internal and external projection, add some types of lifting lugs, hand grips, manways, and stud bolts. So let's add a hand grip, M2 grip. And from here you can select the suitable type. You will find different types, like this type of hand grip, or this type of hand grip, which is welded to the outside diameter of the cover, or that type of. Yes,
I have a question before we pass the topic of flanges.
Yeah.
The orientation option in flanges, this refers to if it is straddle or center line, and if we can add a value in orientation box.
Yes. Okay. If we come back here to the facing of the flange, you can figure that the holes now they are
straddle.
Straddle option, sorry.
So the default is straddle.
The default, which is 0. On the 0 value, it will be straddle like that.
Yes.
Not intersect with the original axis.
Yes, yes.
Okay. But if you would like to control that value, you can change the orientation. This option gives you the ability, if you have a nozzle over blind, okay, and
yes.
This nozzle takes an orientation, like, let's create a new one. So if we have a cover like that, and you have a nozzle on 45 degrees here.
Yeah.
And you add, a flange to this nozzle. So this nozzle will, the holes will be straddled on the perpendicular axis, that one, not the other original. It will not be straddled to those axes. It will be straddled to the orientation axis, the black axis. So if you would like to rotate the flange, you can control them by using the orientation option for the holes. I hope this point become clear. We can try it on a vertical nozzle. Let's make a huge diameter size nozzle and make a cover. After that, we can add a nozzle over this cover to show you what I would like to say here.
Okay, I got it, but you talk about if it is a secondary nozzle over a main nozzle.
Yes, or over
Correct?
a cover. Yes, or over a cover.
But my question was about the main nozzle, like the nozzle we already created.
It's this concept
if I
for
want
any
it
nozzle.
to be centered.
This concept for any nozzle.
Yeah, okay.
Yes.
So
but
same
I'm
concept,
talking about
same concept for main or
easily,
secondary. It's the main concept.
Yes, it's a main concept.
Yeah, okay.
But
okay,
I'm talking here in that case, if you have a nozzle with, let's say, 60 degrees or 45 degrees on a cover, nozzle on a cover. Okay.
Yes, I got
and so if you add the flanges, the straddle holes will be straddled to those center lines, not to those center lines. They will not be
not the perpendicular center line.
Yes, not the original. They will be straddled to the nozzle orientation. Okay, so if you would like to adjust them, you can do that from the orientation button. Text.
Okay, orientation text. Mr. Ahmed, can I ask one question?
Sure.
We use compress software. Is it possible we can import compressed data in SEG and make the model, preliminary model?
Actually, right now, not this option is not completed yet. We, from more than, let's say, 1 year, we start proceeding making an integration tool with the exported XML file from Compress. Okay, but this tool we didn't finish it yet. It's still under testing. But inshallah, after finishing it, you can read the exported XML file from Compress to generate this tree automatically. So instead of creating this tree manually, this tree will be generated automatically.
When we can expect that?
Maybe 6 months, maybe. But because we are facing some issues, and we are asking the technical team for Codeware to support us in that, so we still waiting some response from them.
Okay.
Okay, here let's come back to the hand grip, and let's select the first type, define the length, define the width, the rod diameter, the offset from the center line, and let's add 2 hand grips. And from here, let's click start. Simply. Okay, now we have those 2 hand grips here. Now let's add stud bolts. So let's select the blind flange. As mentioned, we select the main parts. So the blind is, or the cover is a standard, or the cover is a main part. Here you can figure that it's a main part. So when you select it, you will find the available attachments to this element. Now let's add a stud bolt. So M2 From here, you can select between ISO standard and UNC standard. From here, let's select 2.5 inches, define the material of nuts and bolts, the stud length, the length of the stud, and from here, the nut spacing, which is the spacing between faces of nuts, so we can measure it from here. We have this blind to the other one. So that's the projection, the spacing between nuts. So we can define it here. And we click on save. Now if you click on start, SEG will create the tightening studs seats. Here we have this manhole with bolts and hand grips. Now, if you would like to add a davit, you have two different types, and if you would like to add your own davit, you can do that. But let's discuss the available types of davits here in SEG. You will find manway davit and manway detailed davit. The difference between them, the manway davit will give you the davit as a one part, not a detailed part. So it will appear on the bill of material as a single part. Davit. Okay. But in detailed manway davit, you will be able to get a detailed bill of material for the manway. So let's try the first part. After that, we can try the second part. For the manway davit, M2 davit 1. You can figure that you can select from different types and the configurations here. Okay, the suitable type for your case, but be sure that it will appear on the bill of material as a single part. Like here, let's keep this orientation as it is and click on save. Now if you click on start assembly, so this part will be generated like that. Just we need to rotate it 180 degrees because it's flipped. Okay, so we need to rotate it like that and start assembly. As you can see, if we open this davit from here, it's a single part on the tree. It's a single part like that, created from features like that. And on SEG bill of material, if we open the bill of material table, the davit will appear like that. So if you take a look to this row, that's the davit. It appears as a single part. So it's a manway davit type H, detailed drawing. So you can, if you have a detailed drawing for that in AutoCAD or in Inventor, you can refer it here. So that's an assembly, not a detailed part, and that's the weight of the davit. So you can figure that it's a single part. In case if you would like to make a detailed davit, in that case you will find a detailed davit from here. Let's say M2. And from here you will find some standard specs. You can select from them, and if you would like to modify on those dimensions, you can do. For example, for that standard, or let's select another one like that. If you select that, you can select the rating and the size of the flange. As you can see on this standard, no 24 inches with a rating 900. If we select this type, for example, and you can figure that based on this standard, the available rating up to 600, but you will find different sizes. So in case if you would like to make a modification on the dimensions of this one, here you will find an option here. This is a checkbox, which is user defined dimensions. If you select it, all of those values will be directly open to you. So you can define the all dimensions here manually. Okay, if you have some calculations, so you can modify on that one. The same for that one. If you have this size but 20 inches, so you can make a user defined and define the flange thickness and a dimension according to this drawing. After that, you will generate this item and you will get a detailed bill of material. So if we save this, but let's don't create it, but for here, you can figure that you have a washer, nut, eye bolt, David arm, and David clip, lug, and David support ring, David support lug. So you will get a detailed bill of material for this manway, David. So let's delete it. So now you have an idea about the difference between the detailed manway and manway as a part. Okay. Now let's add another nozzle to this manway to show you what the difference between the orientation of the holes, because we discussed that here. So if we select this manhole and from elements, let's add another nozzle. So from here, let's add N1, for example. We have this nozzle on the cover. Okay, and let's add, okay, let's add this nozzle as 2 inches with 40, K80, K, and offset, let's say like that. Projection, K, and N1 flange, N1 flange. Okay, so it's inches. Sorry, wrist face, 2 inches, and with scalable 80. Click save. I would like to check the orientation of this nozzle. Yes, let's make it on 45 degrees. Now, when we generate this nozzle, you can figure that here the holes, if we make a view, if we make a view from the other view here and make it without hidden lines, you can figure that the main orientation of the nozzle, and we have another axis here. So those holes are straddled to the original or the the orientation degree of the nozzle itself, not the main element. So to control that and make the holes straddle to the main axis, here, you will need to rotate those holes on flanges with 45 degrees. So if we select this flange here and make this value is 45, click on save. If you click start assembly, and if you come back to the drawing, you can figure that the holes shall be straddled to the main, to the main to the main axis. Okay, not the nozzle orientation axis. I hope now this point, after applying it, become clear. Okay. Hello.
Clear, Mr. Ahmed.
Now let's add another helicide nozzle on this head, or let's add another nozzles on shell, okay, with some helicide nozzles on shell and radial nozzle. So from here, let's select CAN 1, and from here, let's add N3, and N3 will be the self-reinforcement standard forged hub. Select the size, the scalable, and the orientation, location and orientation, and the hub dimensions, hub thickness, the insert bed width, the thickness of the shell. So we should insert the shell thickness here, or if the insert bed thickness more than the shell thickness, you can define that from here. This nozzle as it, for example, and the projection we will keep it as it is, make it as a radial nozzle, and let's add a flange to this nozzle, which is in flange. And from here, let's select RTJ, select the rating, the size, and the same schedule, and click save. And let's come back to the nozzle and define the projection of this nozzle. From the calculator, let's define the projection. So that's projection of the nozzle from the mid-center line. So we can increase this value a little bit. So from calculator, and we will get that. So we have nozzle in 3. Let's add another nozzle and generate them in one time. K1 another size. So let's make it with as a self-reinforcement standard forged hub, 2 inches, and with 80 as a schedule, 80, and the location will be orientation 180 degrees. The hub height 55 or 9.8, and the width shell thickness, and click on save. Now let's add a flange to this one. So K1B flange. Select RTJ, select the rating, size, and schedule. If we come back to the nozzle, we can define the projection. So from the calculator, define the projection. Okay. Projection value cannot be lower than 0. Okay, so from here, okay, So that's the projection of this pipe. Now let's add some of let's add a manway, a vertical manway, and add a nozzle with internal projection to this manway, or this nozzle with cover, and check how we can add connections to this internal nozzle projection. Now let's add a manway from here. Let's add CAN1. So let's add from N1. Let's select it as self-reinforcement standard forged hub. Select the size. Select rating. Scalable, sorry. From here, the location. At 0 degree. Hub dimensions. The shell. Okay. And click save. Now let's add a flange. One flange. And from here, let's make it looks like the flange on the other manway, which is M1 flange. So if we select here, we are selecting M1, so we can select it to make it looks like M2, and click on save. Now let's add another gasket. So M1 gasket. For that, add it. Don't select this option, because if you select it like that, it will be comes after the gasket on this tree for M2. So to add it on the right place, don't select this checkbox. So it will comes here. After creating it, you can change, make it looks like a gasket on flange M2. Let's add a cover, M1 cover. That make it looks like cover on blind knee. Now let's generate those elements. So here, let's check the forged hub here. The dimensions, I think there is something not correct. Yes, the projection, we didn't define the projection. So we need to define the projection, and be sure that you should the assembly is done before making any saving. So from here, let's define the projection and click on calculate. Now let's save this one and click on start assembly to update the forged hub dimensions. Here, I think we still need to increase the projection of this forged hub.
You can save, Mr. Ahmed. You save.
Yes.
Save.
Not what?
You have to make save before start.
I didn't make save?
Save.
Okay, sorry.
Down. You have to make save in the main menu.
Which main menu you are talking about?
Yes, this menu.
This one?
Yes.
Yes, I make a save, but I need to increase this value a little bit. And from here, let's reset this element. Because if we have an error on the sketch, it will be generated again. I think it's okay now. Okay, now let's add another nozzle to the blind, to the cover, and this nozzle will goes to inside, and let's make some piping for this nozzle. So from here, let's select this cover, and from elements, let's select nozzle with internal and external projection, this type of nozzle. So let's make it as N2. And from here, let's make it a nozzle from pipe. Let's make it from 4 inches with a scalable 80 with rebad. Okay. And make it as the center of the nozzle. Make the projection to the outside like that, and 2 inside with 1 meter. Click on save. Now let's add a flange to, or let's add an elbow to outside. So into elbow 1. So we have an external, at the external point we have an elbow. So let's select a long radius with 90 degrees. And from here select the size as 4 inches. Select the schedule and click on save. And let's add a T to the internal connection of the nozzle. So from here let's add a T. So into T1. As you can figure, let's make a print screen and that here in detail. You can figure that this type of nozzle, which is in the 2, includes 2 connection points, which is internal and external. So you can add attachments to the internal end of the pipe and the external end of this nozzle. And if you take a look to the T here, you can figure that you have 2 connections, a branch and inlet, and you can change the connection point for this T if it's connected to the pipe from the branch or from the inlet. And let's discuss that here on the model. But first, let's make it as equal T and make it with the 4 inches with this schedule. Okay, and click on save. Now, if we click on start assembly, we will generate a nozzle on the cover. After that, SEG will generate a T connected to the end point of the nozzle and the elbow at the outside point of this nozzle. Okay, that's the elbow. Now let's take a section. So from view, let's take a half section. Like that, you can see that this elbow connected to the end of the pipe, like that. And we have the T connected from the inlet to this nozzle. You can control the orientation of each element like this elbow or T from the orientation button, but we need to discuss the option of T connection. Here, this T connected to the end of the pipe from the inlet side. If you would like to connect it from the branch, just select connected from branch, this option, just select it from here. And let's select change the size to or change the type of this T to make it as a reduced T, make it 8 by 4. like that, and make it connected from branch. So the 4 inches size will be connected to the end of this one. And let's click on save. Now you can, if you click on start simply, you can figure that this T now connected from the branch, not from the inlet, and we make the 4 inches connected to the 4 inches. And now let's control the orientation. So let's rotate it by 90 degrees. So if you click on start, now the orientation of the T changed to be like that. Now you can add elements to this connection point and that connection point. And you can figure that you have inlet 1 and the inlet 2, because now the branch is connected to the nozzle. So you have 2 inlets, this inlet and the inlet at the right side and the inlet on the left hand side. No branch right now because the branch is connected to the nozzle. So you will find inlet 1 and inlet 2. Now let's add a reducer here to reducer 1. And from here, let's make a centric cone with 8. That's the scalable by 4. And that's the scalable. And let's add an elbow to the other side. So in 2. And let's make it 45 degrees. And this elbow will be 8 inches. And will be with that scalable. And let's click on save. Now let's run this simply. Now you can figure that you will get a zoom extend automatically for the view. If you would like to remove this option and make zooming manually, you can control that from the setting button here. If we open the app setting, you can make the zooming by selecting normal option. Okay, and let's zoom like that. And when you change the orientation of this elbow, like that, and click on start simply, no zooming out will take place after updating the 3D model, like that. So no change on the zoom in or zoom out automatically. So let's change this orientation to 90 degrees. And let's add a pipe after this elbow. So you can add to pipe 1. Find it as 8 inches pipe with the scalable 80 with a length 400. And let's add a flange to it. So in flange 1. Let's make it as a slip-on or a slip-on flange 300 and the size 80, 15 millimeters lap. Okay, let's add a gasket to this one. So gasket 1. Raised face 300 and the size. Okay, let's add another flange. So in flange and let's make it looks like flange 1 into flange 1, but we will make it as a flipped flange. So let's come back to the flange and make it flipped. Now let's add let's say a valve. Okay, we could add a valve. So instead of this flange, let's delete this flange and add a valve. So let's add a valve after this one. So from here, from elements, let's add a valve in valve. Let's select check swing valve rating 300, and that's the size, and click save. Now if you click on start assembly, the elbow orientation will be changing to come down. After that, we have a pipe with 400 millimeters length. Clip on flange. Gasket. After that, a flanged valve. We can control the orientation of this valve. Let's make it 90 degree. Save and reassembly. Okay, now you have an idea about creating internal and external connections to the nozzles. They are the same concept. Now let's add some helicide nozzles to this vessel. Okay, so let's come back here, and for CAN 1, let's add nozzle A to A. It will be a self-reinforcement forged hub nozzle. Sorry. Okay, select the schedule and the location of this one and the orientation. But it's not a radial nozzle. Let's make it a helicide nozzle. And from here, let's define the offset as 300, and the orientation will be in a counterclockwise. Okay, let's define the up height, thickness, and the width, shell thickness, and let's click on save. Let's add a flange, B2A flange. RTJ, select the rating, size, and the same schedule. If we come back to this nozzle, and from the calculator, let's create direction. The direction for this helicide nozzle. Now let's click on save and start the assembly. Okay, now we have this nozzle as a helicide nozzle, and the direction of offset, as we discussed, the orientation, it's a counterclockwise. So it will not be on that side, it will be on the top side because it's counterclockwise. Okay, let's add another nozzle. So from here, let's select CAN 1 and add K2B. Okay, and from here, let's make it looks like K2A. Okay, and I will show you if you make it same as during importing. If you consider that this nozzle has an external connection. Okay, so let's delete it and add it. But in that time, we will add it as same as K2A. So from here, K2B. But let's make it looks like K2B. You can figure that this nozzle comes here without the external connection point. Okay, so we not recommend using this type unless if you have a long weld neck nozzle and no connections to this nozzle. So to create this nozzle in a correct way, looks like K2A, you can make those steps like that, K2B, click add. After that, from here, you will find below this image an option gives you the ability to make it looks like another nozzle. The same here. Let's add a flange, A to B flange. After adding it, make it looks like K to A flange. And now if you create it, it will be located on the same location of the nozzle, but actually it's in a different offset. It takes the same location, the same orientation, but with a different offset. So it's on 400 millimeters with the same projection. So if we calculate that, the projection of the nozzle will be changed. So the value here will be calculated again if we click on run assembly. So I think we need to increase the offset a little bit. So let's make it, let's make it on clockwise, not counterclockwise. It's below, so let's change it to be clockwise and click on start. Now let's add another nozzle with more offset. So let's select N1 and from elements let's add KA. Let's make it looks like K to B. After that, we will modify it. Let's add another flange. A. Flange. It looks like K to B. And when you come back to this nozzle, you will be able to define the location, orientation, all of that, but we will change the offset of this one, 1200, and let's keep it on counterclockwise. Now let's click the new nozzle with this offset. So if we open this forged hub as a separate here, you can figure that if we take a look to this part from that side, and let's take an image of it and put it here. You can figure that the inside diameter of this, the whole of this one here comes like that. And if you measure this straight edge here, if we increase the thickness and change the color, this edge here and that one and that one there, okay, those are with the same value, which is the width of the wear plate or insert bed. For this insert bed, those values are the same. But regarding the huge thickness of this vessel, which is 118, you can figure that you will get two different ends here. This length will not equal that one. This will appear clearly for nozzles with large offset and with vessels with large thickness. This configuration, you will detect it easily. Okay, so let's make another nozzle with a large helicide offset. By the way, before going to the next point, here if we take another here and get another one, the length here, same here, there, and there. Anywhere you will get the same width for this insert bed as the outside surface of this nozzle. But as you can figure, at the inlet, it will not be the same. This line, if we come back here, this line, if we create a new line with the red color here, this line goes to the center of the vessel. If you make a lines here, so the cut of that will be perpendicular to the surface of the shell. Okay, so let's make another nozzle with huge offset. So from here, let's create a new nozzle. Let's make it as K5. Okay. Let's make this K5 like K3A. Okay. And flange for this one. K5. And heading it. K3 A flange. If we come back to nozzle K5, let's define the offset like that. Okay. And change the orientation, change the direction to be counterclockwise. So we change those values and click on save. Now let's modify the projection and calculate the projection of the pipe, and let's click on save. Now when we click on create, we will get another nozzle on the other side. Okay, we keep the dimensions as they are, but here if you take a look to this one, if we open it, you can figure that the hole comes out this insert band. The width is still the same here and there, but if we make that one with shaded edges or as a wireframe, you can figure that the hole or the opening through that one comes out from the wear plate. To solve that, you will need to increase the width of this pad. If we increase it to 300, for example, and update the model, and open that part again, you can figure that, let's make it frame again, you can figure that the width of this insert bed is okay from inside and outside, and the same point that we talked about, which is you cannot get the same offset from here and there because that surface goes to the center of the vessel. Okay, so I hope this point become clear for you now, and we have, I think, 50 minutes for discussion, and inshallah tomorrow we can add an extra elements by not included in SEG, and inshallah we can make our own border and the title block to use it in this project. After that, we will proceed with drawings. Today, inshallah, we have 15 minutes. We can make it for discussion. Any questions?
Ahmed Wahid having some issues with modeling. Can you, Ahmed, share your 3D modeling? Ahmed Wahid? Wahid? Ahmed Wahid? Just unmute yourself.
No problem.